All right, this week's concept is going to be looking at primarily net ionic equations. Okay, and before we get into net ionic equations, we have to understand how ionic substances, what they do when they're placed into water. And if an ionic solid is soluble in water, it will not only dissolve, it will dissociate. So dissociation, vocabulary term, is that the ionic compound, when it is placed in water, its ions will separate, its positive and negative ions will separate apart due to its interaction with water being polar, and that will cause the ionic compound to now be as separate ions floating around into the water. And again, this process is called dissociation. Before you can do dissociation equations, you first have to determine is the ionic compound soluble in water? Well, this is where you're going to want to have your chem helper out. So if you have your chem helper out, on the very, very top of the chem helper where we have all of the equations, there's a solubility table. And being able to read that solubility table is going to be very important and crucial for this whole week. Now, you'll notice that the table is organized so that along the top it has the anions. So whenever you have an ionic compound, remember there's going to be a positive and a negative particle. You want to look at the second half of the compound, the anion, not the cation. Look it up and then use the table to determine, which substance is soluble in which. Okay, so we're going to get some practice doing this now. And so down below I've given you 6 ionic compounds. And we know they're ionic for a couple different ways. First, does it have a metal? If it starts with a metal and has a non-metal, it's an ionic compound. If we see parentheses lets us know that there's a polyatomic ion present. There's an ionic compound. So that's how we got to be able to first identify if it's an ionic compound or not. All right, so for the first one, AgCl, silver chloride, we're going to look up the chloride ion, the Cl ion. And you'll notice it's about in the middle of the table, okay? And it says, right below it, in the soluble column, it says most are soluble, okay? The ones that are insoluble are silver, lead, mercury 1, copper 1, and thallium 1, okay? Well, you'll notice that silver is one of the choices given that is not in the soluble column, but the insoluble column. So silver chloride meets the insoluble column, so therefore this substance will not be soluble in water. Okay, so we would put down not soluble. Okay, so now if you want to go ahead and practice doing the next 5, looking up the negative ion first and then seeing with the positive ion, does it meet the soluble column or the insoluble column, get practice doing this. So go ahead, pause the presentation now. Go ahead and see if you get the correct answers, and then I'll go through the answers quickly now. All right, silver nitrate should be soluble because it says all nitrates are soluble. Silver acetate, C2H3O2, is called acetate, and again it says most are soluble. The only ones that aren't are silver and mercury. Lead is not one of them, so this will also be soluble. Calcium hydroxide. Hydroxide, it says group 1. Group 1 means any metal in the first vertical column periodic table. The group 1 metals, the alkali metals, all of them are soluble. Ammonium hydroxide is soluble, and strontium, barium, and thallium. You'll notice that calcium is not in that category, so therefore it must meet the insoluble column because it's not one of the cation combinations that makes it soluble. Sulfide, S, is the third to last column. It says group 1, group 2, and ammonium sulfides are soluble. Ammonium is with the soluble column, so it'll be soluble. Lastly, barium sulfate. If we look up sulfate, which is the 4th column from the end, sulfate it says most are soluble. Insoluble ions, you'll notice in the insoluble column, barium is one of the insoluble ions. So therefore, the combination of barium sulfate is insoluble. Okay, so again, make sure you can identify if it's soluble or not. Okay, all right, the next step, once you identify if a substance is soluble or not, the next step is being able to write a dissociation equation. Dissociation equation simply means that when we put that ionic solid, sodium chloride is a solid at room temperature, when I put that solid into water, so I'm going to draw an arrow and I'm going to put water over the arrow. Now, the most common mistake students make here is they want to put water as a reactant. It does not react with water. Water helps dissociate it. There's still sodium ions and chloride ions. The difference is instead of now them being put together in a solid lattice, it is now separated into individual ions. So the water is the medium at which the sodium chloride can dissociate. So all you've got to do now is separate the sodium and the chloride, but it doesn't separate into neutral atoms, it separates into ions. When you are done, the sum of all of the ions should add to 0 because the ionic compound is a neutral particle with charges. So plus 1, -1 add to 0. So that is a dissociation equation for sodium chloride, being able to break it apart into its individual positive and negative ions. Just make sure they add up to 0. All right, if you want to pause the lecture and try to do the next two, please do. Otherwise, just follow along. All right, potassium sulfate. Again, if you're asked to do dissociation equation, all you're going to do now is put water over the arrow and you're going to break it apart into its ions. You have to be able to identify who the positive and negative ions are. So here we have potassium and we have sulfate. If you have to look at the ion table in the Chem Helper, please do, but the charge on potassium ions are +1 and sulfate is -2. Right now, if you looked at it, you'll notice that the sum of the ions would not add to 0. They would add to -1. But you can't forget that potassium, there's a 2 there. The 2 is there because of cross-dropping of charges to make sure that it's balanced. Now, instead of putting the 2 after the potassium, we put it out in front. Potassium sulfate will dissociate into 2 potassium ions for every 1 sulfate ion. It's a 2-to-1 ratio because we need the 2 positives to cancel out the 1 -2 ion. Lead 2 acetate. The lead is +2. I know that because the charge on acetate, C2H3O2, if you look at the ion table, is -1. But there's 2 of them. And again, now the subscript becomes a coefficient when we dissociate. We need 2 acetate ions. Each one is a -1. That adds up to -2. So the lead must be +2 to balance the charge. So that's probably one of the hardest things in this unit, is to be able to separate the ionic salts into the appropriate ions and their appropriate number of ions. But when you are done, all of the ions that you've put down, the positive, negative, the sum of them should add up to 0. Now, what prevents these ions from recombining and just staying as a solid? What prevents them? And that process is called solvation. We briefly talked about it last week. But when I have a substance like sodium chloride, okay, all right, water molecules are polar, and that's because water is bent, creating a negative end, which is along the oxygen, and a positive end, which is around the hydrogen. And because water is polar, its poles are attracted to the individual ions. Well, what part of water do you think is going to be attracted to the sodium ions? Hopefully you said oxygen. So what will happen is the oxygen part of water will get closer to the sodium ions, and multiple water molecules will attract and surround that positive ion. And that process of the polar water molecules surrounding each of the ions is called solvation. And this is how the sodium chloride bond can break. The water molecules, in essence, attach to the ions and literally pull them off of each other, separating them into their ions. And that's called solvation. For the negative ions, it's the opposite. The positive part of water is more attracted. So the hydrogens should be closer than the oxygens. And that's how the negative ion is surrounded. Okay? So this process is called solvation. And because water molecules get in between, now the ions can't simply recombine and reprecipitate out of the solution. This process is called solvation. The stronger the attraction of the water molecules to the ions is, the more soluble that material is, because this process will be more and more likely to occur. Okay? Now, if we look at this, now we should be able to look at something called ion concentration. What is the concentration of the individual ions in the solution? And something interesting happens with that. So if we look at the next page, or yours might be the one right below this, there should be a picture. So we have a solution of aluminum nitrate. So when we put aluminum nitrate in water, it will dissociate into +3 aluminum ions and -1 nitrate ions. So if I've got a water up here, and this is a solution of aluminum nitrate, you are going to be seeing aluminum +3 ions floating around and nitrate ions. Now here's the question. Would the ratio of aluminum ions to nitrate ions be 1:1? It should not be. The nitrate ions, there needs to be 3 of them for every aluminum ion because of the charge. The solution still should be neutral in charge because we just made positive charges, negative charge. There shouldn't be a differential in charges. So if I wanted to draw this picture correctly, I would need to make sure if there's 2 aluminum ions, that there would be 6 nitrate ions for the 2 aluminum ions. The ratio always has to be 1:3. So you have to be concerned with the dissociation equations of what that'll do. Now, because there's 3 times as many nitrate ions, the concentration of the nitrate in the water is going to be 3 times that of the aluminum. So if I know the concentration of the aluminum nitrate, if the bottle of aluminum nitrate says this solution is 0.25 molar, that means there are 0.25 moles of aluminum nitrate in every liter of water. The concentration of the aluminum nitrate, if it's 0.25 molar, how will the concentration of individual aluminum ions compare to aluminum nitrate? It's exactly the same. Why? And that's because for every 1 aluminum nitrate molecule, there is 1 aluminum ion that is produced. When the ratio is 1:1, the concentration of the compound is going to be equal to the concentration of the ion if we get 1 ion of it per molecule. The nitrate is not. The nitrate, we're getting 3 times as many nitrate ions as aluminum nitrate particles, and therefore its concentration will be 3 times as big for a total of 0.75 molar. If the question is what is the total ion concentration, we would now have to add up the aluminum ions with the nitrate ions for a total of 1. The concentration of all ions, we're producing 4 ions for every compound, and therefore the concentration of the ions in the solution will be 4 times as much as what the concentration of the aluminum nitrate in water would be by itself. So concentration of ions, you have to take into account the stoichiometry to be able to look at its concentrations. Something just to be concerned with. And you'll have some homework examples off of that as practice. The last thing is now we understand how ions separate and dissociate into particles and the numbers of them that they break apart into. Now let's look at how we can do what's called precipitation reaction. A precipitation reaction is one in which we have 2 aqueous solutions that are mixed together to produce an insoluble solid. So therefore, when we mix the solutions together into a beaker, we'll see a precipitate form where it'll crystallize out of the solution, forming a pile of solid on the bottom. These are called precipitation reactions. And that's because one of the products produced is not soluble in water, and therefore it precipitates out of the solution, forming the solid that you see. These are called precipitation reactions. Now, precipitation reactions are double replacement reactions, which means we're going to have the good old switcheroo, where the A and the X will switch around with the individual ions. We're going to do a double replacement reaction. And when we have a double replacement reaction, the charges on the ions are constant. The charges on the ions don't change. So if the A has a charge of -2, it's going to stay -2 on the product side. Whatever the charge on the reactant side is, that'll be the charge of the ions on the side. All that's going to happen is they're going to replace each other to form 2 new products. The net ionic equation, which is the goal of the rest of this lecture, is to create an equation that shows only the particles that undergo a chemical change. We don't want to include any other particles or ions that simply do nothing in the solution. Those are called spectator ions. So a net ionic equation is an equation that gets rid of all spectator ions, leaving behind only the chemical species that undergo chemical change. So let's go ahead and practice doing an example of a net ionic equation. So write the net ionic equation for the precipitation reaction that takes place between lead 2 nitrate and sodium chloride. The first thing we want to do is write the molecular equation like we did way back several months ago. So lead 2 nitrate, I want to put down the state of the materials. And since they tell us that these are solutions, that tells me that lead nitrate is soluble in water, and therefore it'll be aqueous. Aqueous means it's soluble in water. Sodium chloride is also. So for all of these reactions initially, if they're telling me that they're aqueous solutions, I immediately know that they're aqueous. Now these are a double replacement reactions, so now the lead is going to go with the chloride, and the sodium is going to go with the nitrate. Now this is where we have to look at the ion charges to get the right formula. The sodium is going to be +1, the nitrate is -1. Since the charges match, they are going to form a 1-to-1 ratio. The lead, before the reaction, I know the lead was +2. How do I know that? Well, nitrate is -1, and there's 2 of them. So that tells me that the lead was +2 before the reaction. If it was +2 before the reaction, it stays +2 after the reaction. Chloride ions are always -1, and so we can see here the charges do not match, so we have to cross drop. So the first step is to get the right formulas. All review of writing balanced equations. The next step is to balance the equation. So we have 2 nitrates on the left. We only have 1 nitrate on the right. Again, we always want to balance polyatomic ions first as whole groups. So I got to put a 2 in front of the sodium nitrate, so I get 2 nitrates on both sides. That's going to give me 2 sodium ions, so I come back to the left and put a 2 in from the sodium. That's going to give me 2 chloride ions, which I have 2 chlorides on the right. Lastly, check the lead. 1 lead on the left, 1 lead on the right. We're good. We are balanced. The last thing is to consult the solubility table. Are these 2 ionic compounds soluble in water or insoluble in water? So let's look up lead chloride. If I look up chloride, Cl, right in the middle is the halides, the chloride. It says most are soluble, but lead 2 chloride is insoluble. So therefore, I'm going to put an S after it, which tells me it's an insoluble product. Nitrates. It's the second column. It says nitrates. All are soluble. So if it's soluble, I'm going to label it with an AQ. So anything that's soluble is AQ, aqueous. Anything that's insoluble is labeled with an S, insoluble solid. So right there is the balanced molecular equation that we did way back several months ago. Now, how do I convert this molecular equation into the net ionic equation? The next step is to do what's called the complete ionic equation. In the complete ionic equation, anything that is aqueous, that's an ionic compound, it's soluble in water. And what do soluble ionic compounds do in water? They don't just dissolve, they dissociate. So the next step is to dissociate anything that is an aqueous substance. So anything labeled an AQ, we're going to separate it into its 2 ions. The lead 2 nitrate is going to break apart into lead 2 ions and nitrate ions. Will I get 1 of each? No, there's a 2 after the nitrate because I need 2 nitrates to balance out the +2 charge on the lead. Now, whenever